Good morning. This is Lecture 6 of Mate Technique 2013 at the University of Twente, the Netherlands, and this is Edwin Carlin giving the lecture this year from the University of Tsukuba in Japan. Today, I'm going to discuss basic statistical principles and measurement uncertainty with respect to measurement systems in general that can be used both practicum exercises as well as later in your career as practicing engineers and scientists. Please note that homework assignment 4 is due today, December 12th, 2013, and homework 6 will be available on Blackboard today, so you can download and start doing the exercises. Also, lecture 7 next week on December 9th, 2013 will take place as a regular lecture in Reveline 2504. We will have a guest lecture by Dr. Walter Althaus, and the topic is chemical sensors. So please go to the lecture Reveline 2504, Monday, December 9th, 2013. Dr. Althaus will give a homework assignment and also have a question on the final exam. So following his lecture is quite important. Also note that homework assignment 4 and homework assignment number 6 are both due on December 9th. So please make sure to hand in those homework assignments. Measurement uncertainty, definitions and statistical properties, error types that we'll discuss today, systematic and random, error reduction and quantification, random errors, the idea of probability density functions, and then I will discuss 3 types, although there are many more, and the 3 that I will talk about today are the normal or Gaussian distribution, uniform distribution, which is important for quantization, and Poisson, a Poisson distribution, and I'll give an example of a source of Poisson randomness with a measure n that we will detect. Then the concept of a histogram, and histograms are used to estimate the probability density function from measured data. And then the characteristics of the random variables, the expectation, which is also called the mean or the average, the variance, and the standard deviation, which is a square root of the variance. So I will define standard uncertainty as the standard deviation of the population. I will talk about populations, samples, and the central limit theorem. Now, this is quite an important concept. So we have a population of a random variable, and when we do a measurement, we always take a smaller number of measurements than the real population has. And this affects how we analyze the data, and I'll give examples of that. And also the confidence interval. The confidence in the estimation of the statistical parameters depends on how many samples we make from the original population. And hopefully by the end of the lecture today, this will become clear. And then I'll give an example at the end of evaluating uncertainty of a system that has multiple components. Characterization of errors. So I will define errors as consisting of 2 components, systematic error and a random error. Now, systematic errors are things like drift, fluctuations that cannot be repeated or be reduced during repeated measurements. But these are things that are slowly varying over time that you can typically correct by doing a calibration, by doing repeated measurements, but it can't be reduced. Now, random error is something we always have in our measurements. We can reduce it by doing repeated measurements, but we will always have some sort of random error. We can never really completely get rid of it, which is different than a systematic error. Usually a systematic error, we can do some correction in how we're doing the measurement. If we have some offset in our operational amplifier, we can tune the offset parameter of the operational amplifier to get rid of that systematic error on the output. However, the random error on the output is always going to be there. So we need to be able to estimate the error on the output of our measurement system, and then this establishes our signal to noise ratio, where we always want our signal to be a little bit higher, at least a rule of thumb 3 times higher than the noise that we have at the output. So in systematic errors, these are known, and also we can have some constant random error, but the point here is that it's a constant random error. And these need to be compensated, and I'll show a little bit an example of how to do that. Another important point is that we have errors that are multiplicative, means that they multiply together, or they can add together. These sources can add together depending on where they come within the sensor system. Absolute and relative errors. These are general rules of thumb, and it's good to remember these. So the absolute error is the measure end subtracted from the absolute real value, which we don't always know. And the relative error is the true value minus the measured value divided by the measured value. So that's the relative error. And then percentage error is either the relative or the absolute error multiplied by 100%. And you can see the definitions of E, Z, and X. This is an important definition that you need to remember when you're looking at error. Are you looking at the relative error or the absolute error? Error reporting. So our estimated value is our best estimate, which is our average or our mean, plus or minus some uncertainty in the measurements. How many samples you have from the population, etc. Now, how do we report that? Let's say we have example data that has 4 values, 2.3 second, 2.4, 2.5, 2.4 seconds. The average of that sample size is 2.4, so that's our mean, and our uncertainty in this idealized value is 0.1 seconds, and then we report this by 2.4 plus or minus 0.1 seconds. This is how we report our errors. This is not completely correct because we actually need to compensate for the small sample size, but this is about error reporting, and this is how we report our errors. But be careful when you're analyzing just a few data points like this and then doing this uncertainty calculation. This is actually quantitatively not correct because we have more uncertainty in the estimation of this because the number of samples here that we have 4 comes from a larger population. So typically when we're really reporting error, this uncertainty, we need 30 to 50 samples in order to get close to the ideal value of the standard deviation of the population. But in general, the error reporting goes in this way. So, a rule: the last significant figure in any answer should usually be of the same order of magnitude, for example, the same decimal position as the uncertainty. And you can see an example of 4 that demonstrate this concept. And the 4th one is definitely not correct because you're saying that the mean that you estimate, you can estimate with 2 decimal points, but then the uncertainty you can only estimate you can estimate only with 30. There are no decimal points. There's no precision, so this is nonsense. So there is one exception. If the leading digit in the uncertainty is small, okay, for example 1 or 2, then it may be appropriate to keep one extra figure in the final answer. Okay, so 27.6 plus or minus 1. You could round this up to 28, but then when you're doing this averaging or this rounding, you lose information. So this is one exception to this. So in this case, when you have something like 27.6, where you're kind of in the middle between 27 and 28, it's better to keep some more information about how close you are to the upper bound or the lower bound, where the lower bound would be 27 and the upper bound would be 28. So as I said, we have two error types: deterministic or systematic errors. These are equivalent terms. And then random or stochastic errors. And these are also equivalent terms that you'll see in the literature or in your textbooks. Now, each error type should be considered and analyzed separately because the nature of these and the origin of these is different. So if we're going to make a block diagram of this concept, then our measurement signal xm that we want to measure will have a deterministic error that gets added to it, and also separately a stochastic or random error that gets added to this. And then our measurement system also separately has noise, stochastic or random, and deterministic. So the output is going to contain all of these components, which can either be additive or multiplicative. So the first one is additive, and then depending on the transfer function of your system, then these errors can also be multiplied onto the output. So, additive errors and multiplicative errors. In the first block, you see that xm and xe get added together. And you'll see that yo, our output, then is the transfer function 1 plus the error signal epsilon e, 1 plus epsilon e times the transfer function of the system, and that actually gets multiplied together through the transfer function. Okay, I recommend that you're able to derive that equation on your own. I will give some of them throughout the lecture of the course, but you should go through and make sure that you agree with all of these terms. You agree, why do we have 1 plus epsilon e? And then if you don't understand that, you can send me an email and I will give you an explanation. But you should try to do some of these derivations on your own because that's quite an important part of this course. Origins of systematic or deterministic errors, environmental effects. This could be temperature, humidity, air currents, if it's a windy day. These are disturbances due to the measurement process. Could be instrument wear in time. When you're doing a measurement, the instruments will wear, so you get this slowly moving deterministic or systematic change in your measurement signal that can be corrected. Connection lead failure, temperature vibration, there are many of these. Sources of environmental effects: light, contamination. Remember when we were doing the standards, one of the biggest problems for doing the weight standard is contamination from oxidation or just contaminants in the room that will go on to this platinum iridium ingot piece of material that changes its weight. Vibrations, temperature, humidity, radiation, electromagnetic radiation, magnetic fields. These are all environmental effects, okay? So let's look at disturbances due to a measurement. So this is a measurement system in the upper left-hand corner. We have a voltmeter that consists of a current meter plus source resistance. And then we're going to connect the terminals of the voltmeter to the circuit that we have. And we want to measure the voltage across this output capacitor between points A and B. Okay, so how do we do this? What's an easy way to analyze this? The first thing that we should do is try to represent this complex, which is not so complex, but it has two voltage sources and resistances, and we basically want to measure between point A and B. So what we want to do is we can make an Thevenin equivalent circuit between points A and B that allow us to easily then make a transfer function of the system so we can assess the errors. So the lower left circuit shows the equivalent resistance of, or the equivalent impedance RAB between terminals A and B, where the voltage sources have been shorted. And then we can simply series connect R1, R2, which is in parallel with R3, which is in series with R4, which is in parallel with R5. And then you construct RAB in the center circuit diagram. And then you can also construct the Thevenin equivalent voltage as well from the upper circuit. So then RAB we can compute, and you see the equation in the upper right-hand equation. And then our measurement voltage is going to have an error due to this source resistance in the voltmeter, which is called Rm. And so there will be a voltage that's dropped across that, okay? And that will introduce an error that we want to measure to represent E0. So Em is this voltage divider E0 Rm divided by Rab plus Rm. An example, if we have resistors R1, R2, R3, R4, R5, then we can compute the resistances. And you can see that if we have a source resistance in the voltmeter of 9500 in this situation, then we're going to have a 5% error in our measurement. If we have an input impedance in this case, which is very, very large, you see that we can reduce our measurement error. This is an example of a systematic error that we can compensate to improve our measurement. The reduction of systematic errors, some methods include calibration. Calibration is the measurement of the output for a range of inputs, looking at the response, making a black box transfer function for this system, and then we can find ways to correct for any systematic errors. Method of imposing inputs is compensation or balancing. This is where we use a bridge. High gain feedback can be used to cancel errors, systematic errors in the system. Filtering, electrical filtering of their signals, both pre-filtering and post-filtering. Just correction, post-processing the data, correction of the output. So we know that we have, our operational amplifier has a, not a drift, but a DC component to it. We can later pull this off if we know that we have this DC component on our outputs. We can also do modulation of our signal to remove some of these systematic errors. So calibration, if we have systematic changes due to drifts of the system being measured, calibration is, as I said, process of plotting the output signal as a function of the measurand, what we want to measure, And many computer-controlled systems, many sensor systems have an auto calibration built into this to be able to check to where the sensor is at a particular point in time. You auto-calibrate the transfer function, and then you can do any compensations for your measurement system in real time almost. Okay. So this is an example of an auto-correction calibration with a 3-point measurement. You have a reference signal, which is constant all the time, and then you have your measurement signal. And essentially, this is a process of measuring at different points in time. So you switch the input from the reference to M, and then you try to balance for your systematic errors in the system. And then post-processing, you know that you're going to have this correction factor for R01, Y02, Y01, Y02 divided by Y03 minus Y02. So in this way you can do full elimination of both additive and multiplicative errors, which are constant or very slowly changing. Okay, so go through this derivation on your own to make sure you understand the derivation of this transfer function. This is why in the first few homeworks we spent some time doing the derivation of transfer functions, because they're critical for measurement systems to be able to analyze these quickly without struggling with the algebra or the techniques of deriving the transfer functions. Compensation: if we have a measurement signal plus an interfering signal, one way to do this is adding a sensor, and this additional sensor will respond equally to the interference, not responding to the measure end. Okay, so we have a sensor that basically detects the interfering signal, and then it responds to the measure end with an opposite sign, so that when we combine them together, it subtracts the common error signal, but you can retain your original measurement signal. And basically this is a balanced differential pair of sensors. Okay, and in this example you'll see on the top is this concept of having this correction signal YC that can compensate for your interfering signal XI. Okay. On the bottom, instead of having this signal manually input to the output, Y0, then we have a sensor, we add another sensor S2 that does this compensation with this differential sensor pair directly. So through this example, on the top you'll see that Y0 is equal to Y1 minus YC, and then Y1 is the transfer function X operated on XM plus XI, and then our output becomes Y0 is equal to SXM plus SXI minus YC. And in this case, what we want to do is we want to apply a compensating signal that's essentially the transfer function operating on the interfering signal XI. So if we use a differential pair, then we go through the same process where Y out is equal to Y1 minus Y2. And then we have the expressions for Y1 and Y2. And then at the output, you will see we have, oh, this is an error. So this should be S1 minus S2 multiplied by Xi plus S1 plus S2 multiplied by XM, your measurement signal. And then when we have S1 equal S2, then Y0 is equal to 2 times SXM, which is an easy compensation. You know that you're going to get twice your signal, but we've removed this drift component by adding this second sensor. A complication of this always is how do you make S1 equal S2? So this is always the part creates problems for this type of arrangement. It works quite well, but it's typically a bit more expensive and complicated to make sure that S1 is as close as possible to S2 and it responds in a similar way. So please note the error here on the fourth line of the equation where xm should be replaced with xi. Differential capacitive sensors that we've been seeing in our homework. On the left-hand side, we have this differential the parallel plates, where our constant electrode is located in the center, and then the blue plates will move together, creating this situation where if the bottom plate moves in the negative z direction, then the distance between the middle plate and the top plate is going to be decreased. But then simultaneously, the lower plate will, separation distance of the lower plate and the center plate will be larger. Then the general procedure with this type of sensor system is that we compute delta C, get an expression for this. And also with this type of parallel plate capacitor, you can also derive the delta C by considering how the plate overlap changes with the lateral displacement of delta x. So there will be one of these questions on the exam that includes also the charge integrating amplifier like we had on the homework assignment already. Synchronous demodulation, which we will come back to. This is an example that I've done in my research as well, and we've seen this already, where we use a differential sensor pair. In the upper left-hand picture, you'll see that we have two capacitors, a sensor CS, which has an arrow going through the capacitor, which means that this is our sensing capacitor, CS, and then a reference capacitor. So the reference capacitor is almost identical without any detection. CR is equal to CS. There's no detection event happening. And then we have this synchronous demodulation where we modulate on the lower left. You'll see the input. And then we also multiply a -1 to our reference. So then we want to subtract any noise. And then we take this into the integrating amplifier. You see our RC pair, and then we amplify it. And then at the end, we remove this modulation component by doing synchronous demodulation and then low-pass filter on the output to remove noise on the output. A bridge compensator. So the measurement of small changes with respect to the initial value. And there will be a bridge question on the exam, so I recommend that you understand the differences between a 1 active element bridge, a 2 active element bridge, which is called a half bridge, and a 4 active element bridge, which is called the full bridge. Know the differences, advantages and disadvantages of this bridge. So if we're going to analyze this bridge, we will see that we have resistors or components R1, R2, R3, and R4. Then we can do a combination of divider, and then we can derive the transfer function V out over V in is equal to this combination. Now in equilibrium, all resistances have the same value. So R1 times R4 is equal to R2 times R3. For bridges, as I said, there are 3 possibilities that we'll consider in this class. A 1 active element bridge, or a half bridge, and a 4 active element bridge called a full bridge. So for the single element bridge, you can go through this calculation. You'll see that in this case we have 3 of the resistors that are all given the same value, and only one of the resistors or the element that changes during a sensing event will change. Now, in equilibrium, this delta R is equal to 0, and then the output is equal to 0. Everything cancels, so that's our output. So this balancing or nulling type of an arrangement means that in the balanced state, the output is always 0. When we have a perturbation or a change in one of the sensors, delta R, then the output that we see is just going to be due to that delta R. This is a balanced type of sensing. It's very, very powerful. So for the single element bridge, you can see that we make this approximation that the change delta R over the initial R is divided by this value of 4, but it's an approximation. So this is a nonlinear transfer function. So that's a disadvantage of a single element bridge. The advantage of the single element bridge is that it's quite simple. Right? So you only need one sensor that's changing, and then you have to find other sensors that behave in the same way, okay, when there's no sensing event. So you have to protect them from the measurand that you want to detect. But they have the base, in this case, base resistance value R0, that's very, very close to the sensor value of R0. Okay, then we have the half and full bridge. We use the same transfer function from the bridge configuration. Now for a half bridge, we will have two of the elements changing. One plus delta R and the other minus delta R. And then the remaining two have the same R0 as we had before. Go through the algebra, and then we get the transfer function V out is equal to delta R over 2R times VI. Linear transfer function, it's a compromise between the full bridge and the half bridge, so it's more sensitive. You'll see we have V out is equal to delta R over 2R. It's a linear transfer function. The disadvantage is a bit more complicated because now we have to have two sensors that give a similar change in opposite directions. So the complexity is more than a single, but you have higher sensitivity and you have a linear transfer function. Okay, then we go to a full bridge. And in this case, all the elements are changing. So in this case, 2 and 3 have a plus delta R, and 1 and 4 are going to have a minus delta R. Go through the algebra again, the transfer function delta R over R times VI. We see this is linear. Again, that's an advantage. It has a higher sensitivity than both the half bridge and the single element bridge because we don't have now this, we have 4 times the sensitivity as a single element bridge and 2 times the sensitivity of a half bridge. The advantage is now it becomes even more complex than the half bridge because we have to have 4 sensors that are changing in a similar way, 2 of them plus delta R, 2 of them minus delta R. So it's much more complex, but it's more sensitive and it's linear. So that's quite an advantage. So depending on your application, then you have to choose the bridge that makes the most sense. So advantages of a bridge measurement, you have a large dynamic range, and this comes from the fact that you're balancing this output. In the equilibrium condition, when you have no sensing event, the output is 0. Okay? When you measure a delta R, then you're going to be changing only the amount that you're going to detect. So you're always can calibrate your system to work in this small linear range, and you can have a large dynamic range by just balancing or null based detection. So you can have a linear transfer function if you're using the half and full bridge, almost linear over a certain range if you're using a single element bridge. And you have a stable 0 equilibrium. This is independent of supply voltage and independent of common mode changes, temperatures and movements and these types of things. So it's quite an important measurement technique. And there will be a final exam question on this topic. Feedback, general principle. So in the feedback loop, please be able to make this simple calculation for the feedback loop. and then the change of the feedback loop with respect to the SF, okay, and how it approaches zero. Okay, so the feedback in general reduces multiplicative errors that come through your system. It improves the dynamic behavior. So remember, in your circuits course, that we can tune the system to respond to your input. Okay, so we can make it fast. We can also um, adjust the damping parameter to be able to respond. So we can improve dynamic behavior of our system. Now, prerequisites for effective error reduction, two main points. You need a high forward path transfer, where this S times K is much greater than 1, and always you need a stable feedback path transfer. So remember that when we were working on the Laplace transform, you want in the real imaginary plane that we want our poles to be in a certain location to ensure that we have a stable operation in the time domain. And from the early lectures, we saw this accelerometer, which you will also use in your courses, in your practicum. And essentially, this consists of a mass. And in the accelerometer, this mass is included right on the silicon chip. It's a big piece of silicon that moves when you have a certain acceleration. F is equal to mass times the acceleration. And then we have a differential capacitor that basically measures the movement of that mass, okay? So we measure the capacitance and then a sensor interface, and then we have a charge integrating amplifier that essentially accumulates the charge, and I don't show the feedback capacitors here, but that's essentially what's in the sensor interface, okay? And then we have an actuator on the bottom, in this case, that pushes the mass back to its zero location, okay? So the feedback signal that we detect is the voltage that's required to bring the mass back to its original location. So this is a real feedback path. And then in this case, this is similar to a nulled output in that when the mass changes, we're going to get an output voltage. That output voltage then will drive the mass to come to its original location. So it changes, you can respond, and it brings it back to its 0 point. And then you measure that voltage change due to an acceleration. And then if we make this block diagram of a system located on the bottom, as we saw early on, we can make a block diagram, analyze this, and we can make a transfer function for the system. And in this case, if the transfer function combination HA, HS, and HE are much, much greater than 1, then we can simplify the output transfer function to basically be the inertia and then the actuator on the bottom, okay, that respond to the iteration on the input. And in this case, when you have feedback, the response is independent of the system parameters, the spring, the sensor, the interface, gain factor, and it depends only on the mass and actuator. Right? So the actuator comes from HA, and then you have HI, which is this inertia. This is this block, this mass that's moving, and your input then is your acceleration. And then if we analyze this a little bit more, we see that we can, going into these blocks, we can analyze the system transfer function, which is the delta x over Fs, which is the force that's put onto the spring. And we can analyze these more. Now another method for reducing these errors is prefiltering. And prefiltering means that you filter your signal before the sensing or transduction event. Examples include electrically induced signals. Capacitive, you can do shielding. Or magnetic induction or inductive, you can reduce loop area. It's also a shielding type of measurement. Changes in the environmental temperature, you can isolate your system from temperature changes, so this is a pre-filtering type. Unwanted optical input, put an optical filter that doesn't allow the light to come to your sensor. Mechanical disturbances, which are shocks and vibrations, so you can put this on an air table and cover it from disturbances due to airflow or people walking on the floor, for example. Post-filtering, which means that you filter your signal after transduction, which usually means if we're going to do a sensing event and then convert this into the electrical domain, do our measurement, this means that we're typically going to do post-filtering on an electrical signal. Then we use filtering, low pass, high pass, band pass, first order or high order. You can also do digital filtering if we're using a DSP chip after doing a analog to digital conversion. We can also do digital filtering. Okay. So let's look at now random errors. Random measurement errors are caused by unpredictable variations. So they always exist. We can never get rid of them, but we can reduce them by doing multiple measurements. These are electrical noise and random environmental changes. Thermal noise, for example. Now, distribution of random errors. A quantitative analysis, which means that we actually get numbers that represent our system, is usually performed on several replicate samples. So we measure, we get an output value multiple times, replicates. Okay, we measure, 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 and these are statistically always a little bit different. Okay, this is our, if we have compensated all of our deterministic errors from the system, then we continue to measure, 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 and then we have a mean value, and then a random value. Remember, this is our uncertainty from multiple samples. So how do we report the result for such an experiment when results for the replicates are scattered around a central value? So we measure, 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 and then we take our values and they look all scattered. Okay, so then we have to essentially get the best estimate of our measurement plus some uncertainty. What's the uncertainty in our value in our measurement? So if we look at the measurement of weight of a coin, or for example, we have a single coin, okay, and it has a particular mass. But our measurement system has some error associated with it, okay, and we measure and we get 5 values for this. Now you'll see that when you look at this, then the mean value is going to be really, really close to 3, but we have some random fluctuations. On the right-hand side of the decimal point, this comes in the measurement error introduced to predicting the real weight, the real mass of this particular coin. Okay. Now, the population is a set of all objects in the system being investigated. So there's an infinite number, let's say, of objects in the system being investigated. Our sample is a subset of that big population. So we only measure here 5 times. That's our sample. The population is almost infinite. We can continue to measure days, weeks, whatever you want. That's our population. It's an infinite number. But our sample, we have a finite amount of time, so we have to sample, and we can only sample a certain number of times. Okay? So for a population of random variables, we have probability distributions. Okay? Now, to predict the properties of a population on the basis of a sample, it is necessary to know something about the population's expected distribution around its central value. Okay. Now, the distribution of a population can be represented by plotting the frequency of occurrence of individual values as a function of the values. Okay. Now, such plots are called probability distributions. On the top are examples of distribution functions, which are indicated with a capital F sub A, and A is our random variable. And the bottom two plots are probability distribution functions, which is the derivative of the distribution function with respect to the random variable. Okay. Now in this class we're going to be using this probability density function. And this describes the relative likelihood for a random variable to occur over a particular region. Okay. In this class, we will consider three probability density functions. Although there are many more. There are many more probability density functions. Okay. So the most common that people know about or are aware, and most software such as Excel are based on this normal or Gaussian distribution, which typically represents thermal noise. Okay. Then we have a uniform or a round-off error probability density function. Now this one is important for quantization. So this is typically used for the conversion from analog to digital signals. This is a probability density function that we will use between two levels. Another important one is Poisson, which is event counting. Okay, and we will use this in an example at the end of the lecture today to discuss how that one works. Okay. So from the probability density functions, then we can calculate the expectation, which is also the mean or the average, the variance, and the standard deviation. And the standard deviation is the square root of the variance. Now you start seeing this root mean square importance. Okay, everything comes back to these probabilistic functions, the root mean square. So the root mean, so we have the square, which is variance, and take the square root of this. Okay. All have commonalities associated with them. So in the measures for uncertainty, there are standard computations for the expectation, which is the mean, which is the average, is the integral of the random variable multiplied by the probability density function. Okay, and then the variance is the root mean square, is the mean square. So this is our error minus our mean squared times the probability density function, and then the standard deviation is the square root of the variance. Okay, these are standard computation for these uncertainty computations. Now, depending on the distribution, so how your random variable is distributed, depending on the element that you have, so different sensor elements will respond in a different way. They'll have a different probability density function representing the randomness of their output. We don't know what that is, but we have to make a lot of assumptions, and we'll go through the remainder of the course how we can do that. So the normal distribution, which is called Gaussian distribution, which most people know about, has this general shape, and the probability density function is located on the upper equation, where mu is the expectation and sigma is the standard deviation. Now you'll see equations here for the mean and then for the variance, and you'll see that when we have a function derived in this way, you'll see n is the sample size, or the degree of freedom. If we have an infinite number of samples, then this n, when we compute the variance, and we always have this 1 over n when we have an infinite number, or really large number of samples. This is our degree of freedom. Okay. Now this value n is going to change when we have a lower number, when we try to estimate what this variance is. So this is a theoretically calculated value, but when we're doing a measurement, we are estimating that variance. Okay, how well do we estimate the variance? How well do we estimate the mean is coming in later in the lecture. So you see that in this ideal case, approximately 68% of the values are within one standard deviation of the mean, 95% of the values within two standard deviations, 99.7 values within three standard deviations. And so now if you've heard or read articles when you're talking about Six Sigma quality, it means that you're able to compute something out to almost 100%. So now the uniform distribution has the probability density function located on the lower left, which is 1 divided by b minus a, and 0 otherwise, and then we can compute the mean, the variance, and the standard deviation. So you will use this value for the standard deviation later in your course when we talk about analog to digital conversion in the quantization. And then the Poisson distribution. And then when we have a Poisson distribution, the equation, probability density function equation, is located on the bottom center equation, and then the computation of the mean, variance, and standard deviation. And remember that the Poisson is a distribution for counting events. As I said earlier, our standard uncertainty sigma e is the standard deviation, and we use this as a measure of our uncertainty. And in this case, I use the probability density function for the Gaussian distribution, which is the most commonly used. Now, confidence intervals for populations. And a confidence interval is essentially a definition of how confident are we in our estimation of the mean, or the average value. Okay. Now, if we randomly select a single member from a population, what will be its most likely value? What's its average value? Okay. Now, it was stated that 68% of normally distributed population is found within the range plus or minus 1 sigma. Now, stating this in another way, there is a 68% probability that a member selected at random from a normally distributed population will have a value in the interval mu plus or minus 1 sigma. And in general, then our value that we select will have some mean value plus or minus z sigma, and z represents the confidence interval. So as z changes from 0.5, then the confidence interval is 38%. When it's 1, it's 68%. So this is our 1 sigma. When we're really out high, 3 sigma, 99.73, 3.5. So our confidence grows as our z value gets larger. Okay. Okay, this is where we come to kind of the core of the basic statistical principles, and you will learn something about the central limit theorem in your random probability and statistics course. And this is quite important because in measurement science, we measure things, and we measure a sample of the outputs from a larger population. Okay, we can't measure the entire population because we don't have enough time, don't have enough money, etc. So we always measure a sample from a larger population. So when we cannot study the entire population, or we cannot predict the mathematical form of a probability or a population's probability distribution, we must deduce the distribution from a limited sample of the members of the population. Systems subject to a variety of indeterminate errors will have results that will be approximately normally distributed. That's an assumption that we make. As the number of contributing sources of indeterminate error increases, the results come even closer to approximating a normal distribution. The central limit theorem holds true even if the individual sources of indeterminate error are not normally distributed. Now, the main limitation to the central limit theorem is that the sources of indeterminate error must be independent, which means they must operate on their own. The neighbors don't influence it, and of similar magnitude so that no one source of error dominates the final distribution. So when we want to estimate the mean and the variance, then we take an average, okay, 1 divided by n, and then we add up all of the errors. Now the sample variance you see changes. Now our lead term now is 1 divided by n minus 1. Okay, so and n represents our degree of freedom or the number of sample sizes that we have. And this is quite an important, so we're estimating the sample variance from measurement sample group from an original population. So then we have to include instead now this leading term, which is 1 over n minus 1. Standard deviation then becomes square root of s squared, the sample variance. Then we can also compute the accuracy of estimating the average, and then you can see in these equations with some straightforward algebra. Now, histograms. Statistical inference comprises the use of statistics and random sampling to make inferences concerning the difference distribution of a population. So what this means is that if we have a number of sample measurements, so in this case we have a plot of data, the result, and trials, and each one of these trials is a measurement sample from our population. If we have enough samples, we can construct what's called a histogram, which shows how approximately our random variables will be distributed. Okay, so we can estimate it, but a little tricky, because we do need a large number of samples, and then also we have to estimate this bin width. So this bin width is where each one of the measurement locations are located between this range 20 through 25. And the frequency is the number of samples that are located within a particular bin. And there's no strict rule on how to construct these, but a general rule of thumb, which is the Sturgis rule, is that the number of bins that we have, 1 plus 3.3 log base 10 of the sample size n, as a good starting point. But you have to be careful when computing the histogram, because choosing the bin width is quite critical. So if you choose a bin width, if you're in about the right location for the bin width, then the distribution doesn't change so much, changing the bin width by a small amount. And then we come to this concept of student's t-distribution. And this is called student's t-distribution because student was a pseudonym for a researcher in England at the time who worked for a beer company, a very famous beer company in England at the time. And he also wanted to do academic work, and he was quite interested in statistics and probability theory. And he published his paper under the name of student. And he developed this t-distribution value when you have small sample sizes that affects your estimation of the mean. Okay? So when the number of measurements of a quantity is small, let's say less than 30, less than 50, and statistical analysis of the distribution error is required, then the possible deviation of the mean measurement from the true measurement value can be significant. So if you have a small number of measurements, your ability to estimate that mean gets decreased, okay, because you just have a small sample of the total population. The student t variable expresses the difference between the mean of the small sample and the population mean. So mu is our estimate of the average, which is our estimated average, plus or minus t, and then our estimated variance divided by the square root of n, our sample size. And this shows an example of this. So if we have a 95% confidence interval, and 95% represents the case where you have 2 sigma. Okay, and in this case, in the left column, the degree of freedom is our sample size. So if we have a sample size that goes to infinity, you see the t value then becomes 1.96. But then the square root of n, square root of infinity, then you basically have no error on the estimation of your mean. Then your mu is equal to mu hat. Okay, but if you have a smaller number, you can see that you will get a finite value. So t divided by root of n, so in this case 2.01 divided by the square root of n, plus or minus is actually going to be increased quite a lot. Okay, so let's look at an example. So we're doing a length measurement of 15 samples taken randomly from a large number of samples. So we have a bigger population, we're going to take a small number of samples and we want to analyze this. How close are we to being able to estimate the mean from the larger population? So from that sample, we estimate the mean, mu hat, is equal to 105.4 millimeters. And then our estimated variance, sigma hat, which is equal to the square root of s squared, is equal to 1.9 millimeters. Now we want to express the upper and lower bounds to a confidence interval of 95% on the range in which the mean value lies for the length of the entire batch. Okay, n is equal to 15 degrees of freedom or sample size, and then n minus 1 is equal to 14. Now for a 95% confidence interval with k is equal to 14, gives t is equal to 2.14, as we saw in the table on the previous page. So if we want to compute then our estimation of the mean, you will see that we will compute this, and then mean, our estimation of the mean, will lie within the range 104.3 and 106.5. Then if we take our mu hat, this is 105.4 plus or minus 1.1 millimeter. So the number of samples that you have critically determines, when you do the estimation of the mean, the range in which you're able to actually. So this is quite an important part, this student t. Okay. So let's do an example to wrap up the course, the lecture today. We have a rain measurement system which consists of a pressure sensor. Of course, the rain is our measurand, the raindrops. The pressure sensor measures the weight of the rain collected in a beaker. So the raindrops are in this blue inside this little container that's sitting on a pressure sensor. And remember that the pressure depends on the height in that container, and we'll talk about that. Then we have a pressure sensor that gives an analog voltage, depending on the pressure, depending on the weight of water that's sitting in the beaker, and the readout unit takes the analog voltage and gives it a digital representation and a numerical display. We assess the uncertainty of this system. In general, there are two ways that we can take. Type A evaluation, statistical inference. Every component in the system, we will run statistical tests, input and output tests, to look at the random variable, how the output is going to vary with the input over all conditions that our system will see. So each component that we have, the pressure sensor, the beaker collection of the raindrops, our analog to digital conversion system, our display, etc., all of those individual components or systems have to be evaluated for all of the noise that the systems will see, statistical inference. Or we can do a type B evaluation where we get information from a variety of sources. Let's say the pressure sensor data sheet will have typical values, and then it will have a range. Okay, we can use those ranges. And then in this we have to use a combined uncertainty, use error propagation, and then we can basically have an error budget for our system that allows us to design a system that's going to give us some certainty of a particular type of measurement. Okay, so type A evaluation, statistical inference, comprises the use of statistics and random sampling to make inferences concerning some unknown aspect of a population. Okay, find estimates for the expectation and variance of the error. What is the accuracy of the element estimates of the individual components? Okay, so you're going to have to go through and do a lot of testing on these. It's really quite impractical. In the type B, we use a combination of sources. Manufacturer specification of a device, handbooks, certifications of a product, general knowledge about the physical processes involved. So in reality, you have a combination of type A and type B, okay? And in the practical sense, you have to design your system with all information that's available for each one of the components in order to be able to do it in a reasonable amount of time. Okay, so let's start. Manufacturer specifications. So the pressure sensor has some characteristics. This is an APX 2910. The pressure range, 0 on max in kilopascal. Full scale span of the voltage. Okay, so typical is 25. The min and max, 24 and 26 millivolts. Now we have a temperature effect on the offset, which we will have a min and maximal value of 0.1, negative 0.1, and plus 0.1 millivolts. So we're going to use the manufacturer specification of the pressure sensor. Now in the raindrop collection, we assume the level after 15 minutes is equal to x is equal to 20 millimeter. This would have to be something that you make some assumptions. Okay, the upper area A is equal to 500 millimeter square. In the drop volume, we assume this to be 100 millimeter cubed, and then we have around, for x equal 20 meters, we have 100 drops. The system model, we have 3 blocks. The input is the level in the beaker, which is 20 millimeters. Y1 is the pressure that the beaker provides. Y2 is the voltage that comes from the sensor. And then our output comes from the analog to digital converter. Now the transfer function, the beaker, S1 is 9.8 Pascal per millimeter. Now remember that the pressure depends on the height of the water. And that pressure is equal to rho, which is the density of water, times G, which is the gravitational constant, H, the level. So you can see that we have 9.8 Pascal per millimeter. Please make that calculation so that that number is clear. Then the pressure sensor S2, which is 2.5 microvolts per Pascal, comes from the data sheet. And then the analog to digital conversion, then we have just the inverse of S1 multiplied by S2. Okay? I2 is then equal to S times X, where S is equal to S1 times S2, and this comes out to be 24.5 microvolts per millimeter. Now the quantum effect of the drops, okay? So as I said, we assume that we have n is equal to 100 drops. Now this drop, this is a counting event, okay? Poisson distribution with lambda equal to 100. Then the error basically is the square root of lambda, which is 10. And then our uncertainty in this, assuming a mean of 20 millimeters, is going to be 2 millimeters. See, the uncertainty in being able to collect the drops on our assumptions is 2 millimeters. So then the error 2, the display and the A to D converter. Okay. The readout unit has a display and an A to D converter. Both display and ADC, analog to digital converter, give rise to quantization errors with uniform distributions. Now assume that the resolution of the display matches that of the ADC, and the least significant digit of the display is 1 millimeter. This is an assumption we make. So delta x is equal to 1 millimeter. And then the uncertainty is our, remember, computed from our probability density function of a uniform distribution, which is delta x divided by the square root of 12. Okay, so then our uncertainty of the display and A to D converter then is 1 over 1 millimeter over square root of 12, which is about 0.3 millimeters. So from the manufacturer specification, we also had a temperature effect. This was uniform, a uniform distribution. The endpoints, this is our A and our B in our calculation earlier. So then the error, the uncertainty, is going to be 0.2 millimeters, the full range, divided by square root of 12, which gives us about 0.06 millivolts. So then we come back to our original block diagram of the system. This is a repeated slide, nothing new. Okay? And then we include our model sources. So in the level now we have our uncertainty of the drops located in the left-hand side of 2 millimeters. And then after the sensor we have a drift term of 60 millivolts, 60 microvolts. And then we have on the right-hand side at the output after the analog to digital converter our quantization error. So then in our output we have some mean value of the level, plus or minus the error, and then we're going to have some uncertainty in our estimation. So for error propagation in a linear case, the rule for error propagation in a linear case is if the error is equal to alpha error 1 plus beta error 2, then the standard deviation is going to be the square root of alpha square sigma from error 1 square plus beta square sigma from error 2 square. Essentially what this means is the variances, the square of the variances sum. So then essentially the total variance of the area of the error E, the total variance of the error E is going to equal to the total variance of each error source, 1 and 2. This is our statement that earlier about the central limit theorem, is that each random variable is statistically independent. And then this allows us to make, in the linear case, that the total error variance is simply the sum of the variances of each individual error component. Okay. Look in our error budget. So we have an error source is the quantum effect of the drops, and our sigma error from the drops is 2 millimeters. The temperature offset, sigma temperature, is 60 microvolts. The round-off error from the A to D converter is 0.3 millimeters. And then the sensitivity of the blocks we had earlier, we assume that for the drops it's 1. This is just a Poisson distribution. The temperature offset, well, we have some mu that we can estimate. And then the analog to digital converter, the sensitivity is 1. Okay. And then the contribution to the variances, then we can sum the squares. Sum of squares, sum of variances. And for each one of these cases, the combined uncertainty, and then you can see that the combined uncertainty for the system is 3.1 millimeter. Okay, that's the combined uncertainty for all of these components. You should go through the calculation of these to be certain that you understand. So then we come back to our characterization of errors, okay, that we saw earlier. And you see that with the random part, we can reduce the effect of random variables with repeated measurements. So we have measurement 1, 2, up to n. And you can see now that when you use this idea of the total variance of the error sources is a combination of the variances of all the individual pieces. Now, when you're looking for the entire system, the systematic or the deterministic errors will not have a value of n for repeated measurements. So you cannot reduce the effect of systematic errors by repeating multiple times. But you can for the random components of the system. And you can compute this by taking the square of all of the variances and dividing the random part by n. So let's do that in our system. We do 10 repeated measurements. Okay, so the quantum effect is random, the temperature offset is constant, and the round-off error from the analog to digital conversion is random. Okay, now we have, if we repeat our measurement 10 times, we can reduce the total combined uncertainty to 2.5 millimeters, which was in our first calculation estimation 3.1 millimeter. You see that our constant value does not change. So that is going to remain constant, and that's quite a large component, the temperature offset, which is a deterministic error, as we said, temperature drifts and these types of things. Okay, so that is the end of the lecture number 6. I recommend that you go through the example at the end to make sure that you understand the numbers that I've given to each one of the blocks for the sensitivity and also for the uncertainty value, which is the standard deviation. And well, not most important, but very importantly, this concept of taking the uncertainty for each of the measurement sources and then being able to add the variances, which is a square of the uncertainty of each of the individual components, to look at the overall uncertainty in the system. And that assumes from the central limit theorem that all of the error sources are independent. And then you can sum all of the variances for the entire system. And then when you want to do repeated measurements, the random components under the square root sign, when you get the uncertainty, will be divided by n, but the deterministic will not. So those cannot be reduced by repeated measurements. Okay, so that's the end of the lecture today. And please remember that the lecture on December 9th, lecture number 7, will be a real lecture in a hall with a real person standing in front of you. Reveline 2504. The details are included on the organization sheet or the syllabus from the course. And homework number 5 and homework number 6 are due on December 9th. So we have 2 homework assignments due on December 9th. That's the end of the lecture today. Thank you.